Hi students, the subject name is EE8353 Electrical Drives and Control. Today we will learn the basic concepts of heating and cooling curve. Before that, we will discuss choice or selection of electrical drives. In this topic is very important to select the electrical drives. The selection of an electric drive depends on a number of factors. Some of the important factors are: first one is steady state operation requirements. In this requirement, there are characteristics is the basic thing. The nature of speed torque characteristics. Next one is speed regulation, speed range, and motor efficiency, duty cycle, quadrants of operation. In this point, quadrants is nothing but is a four quadrant operation. And next one is speed fluctuations. And second important choice is transient operation requirements. In this point, consider the value of acceleration and deceleration. And next one is starting, braking, and reversing performance. These are the important parameters to consider the transient operation requirements. And next, third one is requirements of related to the source. In this point, which type of source we have to use. And next one is magnitude of voltage and voltage fluctuations, power factors, and harmonics. These are the important consideration of requirements related to the power source. And fourth one is capital and running cost and maintenance needs and lifespan. And fifth one is space and weight restrictions. And next one is environment and location. And finally, motor efficiency and reliability. These are the main consideration of choice or selection of electrical drives. And next important topic is selection of a motor drive. In this point, an electrical drive consists of an electrical motor along with associated control and a mechanism for transmission of motion to the working machine. These are the important selection of electrical motors. In this type, the selection of particular type of motor is influenced by its speed torque characteristics, which must match with the speed torque characteristics of the individual load. That means it's a motor load. In selection of a motor drive is further classified into four types: electrical consideration, that means electrical characteristics, and next one is mechanical consideration, size and rating of motors, and final one is cost. These are the important selection of a motor drive. Next important topic is electric motor cooling and heating. First, before that, we are discuss power losses of heating of an electrical motor. In each and every electrical motor consists of the following losses. There are three types of major losses are available in electrical motors. That means this is a power losses. First one is copper loss, second one is core loss, and final one is third one is mechanical loss. Core loss is occurring in armature and field windings, and core loss occurring due to hysteresis in the magnetic materials, and finally mechanical losses due to friction and vintages. These are the major power losses and heating of motors. In each losses occurring in the machine are W is equal to WC plus X square into WV. That means W is nothing but total power loss, WC is nothing but constant losses, WV is a variable loss, X is nothing but load on the motor expressed as a function of rated load. And next important specification of heating and cooling of an electric motor. First consideration is the machine is considered to be a homogeneous body. That means having a uniform temperature gradient. We have considered a body is a homogeneous having a uniform temperature gradient. Second one is heat dissipation taking place is proportional to the difference of temperatures of body and surrounding medium. This is the second important consideration of heating and cooling of an electrical motor. And final one is rate of dissipation of heat is constant at all temperatures. This is the main thing of cooling and heating of a electric motor. First we have assumed heat developed is proportional to the losses we have the heat balance equation. W into dt is equal to A into lambda into theta of dt plus G into S into d theta. W already I told W is the power loss of motor responsible for heat. G is nothing but weight of the active part of the motor. S is nothing but specific heat of the material of the body. A denotes cooling surface area. Lambda denotes specific heat dissipation or emissivity in difference in temperatures. Theta is nothing but is temperature rise of the body, that means the machine body. D theta is nothing but temperature rise in a small interval into dt. This is the basic equation, is called as heat balance equation. W into dt is equal to A lambda theta into dt plus Gs into d theta. It's a basic heat balance equation. Next we have consider the body, the metal machine body have reached maximum temperature rise theta m. So when this condition is reached, d theta is equal to 0. We have considered the value of d theta equal to 0. We have substitute the value in equation 1. So we get the value W is equal to A into lambda into theta m. Theta m is nothing but maximum temperature rise. So we can rewritten as theta m is equal to W by A lambda. We have rearranging the equation number 1. D theta by dt is equal to W by Gs plus A lambda divided by Gs into theta. When motor is cooling condition, the temperature rise would attain a very high value, but theta must be limited to theta m. So we get the equation W into dt is equal to Gs into d theta. And next equation, the linear relationship between temperature rise and time. Therefore we get the value theta by t is equal to W divided by Gs. Tau 1 is nothing but time taken to reach the maximum value theta m, maximum temperature rise. So finally we get theta m divided by tau 1 is equal to W by Gs. Substitute the value of theta m in the above equation. We get the new equation tau 1 is equal to Gs divided by A lambda. Tau 1 is nothing but thermal or heating time constant. In heat balance equation 1 can be rewritten as W minus A lambda theta of T of, that means the differential in time, in particular time dt is equal to Gs into d theta. So we get the value of dt is equal to Gs into d theta divided by W minus A lambda into theta. Integrating the equation, the above equation, both side we have T is equal to minus Gs divided by A lambda of log of W minus A lambda theta minus log of C1. C1 is nothing but constant of integration. So finally we have get the equation E is equal to minus T of A lambda divided by Gs is equal to minus W minus A lambda theta divided by C1. For simplicity, for starting from cold condition, therefore theta, we have substitute the value of theta is equal to 0 at the time period t is equal to 0. So we get the value of C1 is equal to W. So rearranging the equation, we have substitute the value of C1 is equal to W in the equation, above equation. So finally we get the value of theta. Theta is equal to W by A lambda of 1 minus e power minus t of A lambda divided by Gs. This is the basic equation of heating and cooling curve. And initial condition C1 equal to W minus A lambda into theta naught. Theta naught is nothing but temperature, initial temperature rise. So we have substitute the values, finally rearranging the terms, and finally we get the theta value. Theta is equal to theta m of 1 minus e power minus t by tau 1 plus theta naught into e power minus t by tau 1. This is the final equation of heating curve. Next we have calculated the value of cooling curve equation. When a machine That means when a machine is switched off or its load is reduced, it cools down. Each machine have cools down. It cools to the ambient temperature when it is switched off condition. An electrical machine has sufficient overload capacity. Each and every that means each and every electrical machine has sufficient overload capacity. So this because the losses rise more stably than the power. Without cooling system, the motor cannot dissipate the heat to the external medium. Its temperature increases to a very high value. This is the main thing. Without any cooling system, the temperature increases to a very high value. In constant losses remains independent of the load current, whereas variable losses vary as the square of the load. This is the main thing of cooling curve. So the losses will be 0, so power losses will be 0. So total power loss W is equal to 0 in heat power balance equation. In equation number 1 already we will discuss. So substitute the value of W is equal to 0 in equation 1. We get the value 0 is equal to A lambda theta into dt plus GS into d theta. In this cooling curve, we have take a cooling constant, time constant tau 2. So value of theta f means is a falling temperature. So theta f is equal to W1 divided by A lambda. W1 is nothing but total loss at reduced load. So we have finally we get the value of theta is equal to theta m into e power minus t by tau 2 plus theta f into 1 minus e power minus t by tau 2. These are the cooling curve equation of electrical motor. This is the graph of heating and cooling curve. We have take the time as a x-axis and temperature rise theta is taking as a y-axis. We have draw the heating and cooling curve of time versus temperature rise. Okay, thank you.